Okay, so we ran logistic regression, and we looked at some of the interpretation of logistic regression. We looked at what variables were significant in determining whether people got their pizza or not. We also kind of looked at the differences in means for linear discriminant analysis, and now we're actually going to do a tree. So you call for the tree, use the rpart function, dependent variable, whether or not you got the pizza, and all the independent variables. You pass the data set, and we want a class prediction. I remember we can visualize the tree, and we had slightly two different formats. One with the extra equals 2 parameter, and one with the extra equals auto parameter. So let's just see who gets the pizza. So if your number of posts on random acts of pizza at retrieval was less than 1.5, then the vast majority of these, in fact 2,824 out of 3,278, did not get the pizza. So let's just see if you were greater, if you had more posts. And then let's just look at this one. Remember, yes is to the left and no is to the right. Request number of comments at retrieval. So this is the number of comments that your actual your pizza request gets. So I guess if it's not very interesting, like I want pizza, you don't get any requests and you're unlikely to get the pizza. So say, is this less than 1.5? No, it's greater or equal to 1.5. And if my request upvotes minus downvotes at retrieval is less than 13, I go into a non-pizza category. But if I have a lot of if I have a big differential between up and down votes, then 339 out of 441 get the pizza. So this big category of people who got the pizza, they tended to have more posts themselves, their requests got more comments, and their requests got more positive votes, which kind of makes a lot of sense. And let's look at the same categories in like the other visualization. We might as well do a bit of this because there will be, I promise you on the third exam, there'll be lots of tree interpretation. And here it's the same. Remember I said, working out which way the category probabilities go. Here we have a true category, and it's got a 0.88 chance of being true, and it's actually classified as true. And this one's is classified as false, and it has a 0.41 probability. So we can kind of see from that, the one above a half is this one here, and it's true. So this P here is the probability of a true, a true, in this case, wanting a pizza class. So again, let's look through and do the same logic. So if my posts are RAOP at retrieval is less than 1.5, I'm predicted false. 0.14 is true, and I have 81% of the data sets. The majority of the data set, just all these people are just not engaged in the forum. Boom, we're not going to give you any pizza. So let's just do this again. We've got more posts than 1.5 on our AOP. We have more comments on our pizza post, and we have lots of upvotes. And eventually we get to a true category, and in this category we have a 0.88 chance proportion chance or 88% chance of getting true, and this contains 11% of the data. So remember I told you last time in my BQAAnalytics aid, I've got what we call the basic cross-validation function. And the basic cross-validation function, it just runs lots of different data set. It runs on the same data set, but it runs lots of different techniques just to see how well we did. And it records the percentile lift. Recall the percentile lift, if we have, say, a 10 percentile lift, a decile lift, we find, the top 10% predictions, the ones we predict, the 10% of items in the test set that we predict are the most likely to have a true class, and then we see how many of these are true, and we divide this by the proportion of truth in the population. So it's just seeing how good we are at predicting. And as I said, if you have instances where you have very unbalanced data sets and you're never going to get, the majority of, if we only have a few truths in the data set, we're never going to guess the majority of truth. We look in order of which ones we predict, and we just kind of want to see how much better than random we're doing. Very important. And this is probably useful for your homework. So we pass in the in data, the success value. This is not something you copy and paste. This is the success value for your class. So in this case, it's a yes. R is the number of runs we do the kind of cross-validation. And in each of these, it's quite a simple, we're just taking 50% training and test, but we run it lots of times. This is just a more advanced version of the code we've been doing from kind of chapter 6 and chapter 7. And this is the percentile of the lift. So 10% is a decile lift. So let's get it rolling. So we have basic cross-validation. We call the pizza. In this example, a success is a true. And we're going to run it 20 times with a decile lift 20%. Sorry, a decile lift 10%. Okay, so let's let it run, and then I will momentarily stop the video. Okay, so let's have a look at some of our results. So let's just see what we've returned. And remember, with my basic cross-validation, I return accuracy and percentile lift for all of these different techniques. And so we have the linear discriminant analysis, the tree methods, the logistic regression, the random forest, and the adder boost. So let's just kind of look through our results, and they're all doing pretty well. I mean, they're all getting, a decile lift of over 3, which is actually pretty good. And you can see the best. This is just, we've got 20 runs, and we're just calculating the average here. Which one actually has the average? That's number 7. And that's actually the random forest, just slightly better than the others. Recall this second lot are just being added. We're using SMOTE to have like balanced classes on the training data set. And what we can do is, I can kind of summarize the percentile lift, and I'm just doing the first and the last column, which gives me the name and the average. And here we see, yes, the random forest has the best percentile lift. And we look at the accuracy, and again, the random forest has the best accuracy. So that's actually using my little kind of summary code, because again, my code was getting more and more complicated as I was running loops and running lots of techniques in the loops. But this kind of cross-validation code is almost like, if you get your code for your project in the right format, which is the dependent variable called y at the end of the data set, this enables you to do some initial prediction. Now again, let's look at my Carré cross-validation code. And here, and again, I won't go through all the code, but you pass the data, and again, what it does is it just runs Carré, runs repeated cross-validation. So here we'd say have 10-fold cross-validation, and we repeat it a certain number of times. And I don't use any loops here because this is all actually controlled by the Carré train control function. And in fact, Carré actually can run the SMOTE for you. So we actually have a train control, which is repeated cross-validation, number of folds, number of times this is repeated. And then we can have it, and we can also sample with SMOTE. And it will control SMOTE automatically. So again, we have linear discriminant analysis. We train it. Then we have the trees. We have logistic regressions. And yeah, I think for some reason the random forests were misbehaving. So I actually removed this on certain data sets, so I removed this from my code for the moment. But you can certainly play around with that for your project. I think it's because they were like taking too long, maybe. Okay, so let's go back to the pizza run and let's do the carry cross validation and stop my code. So stop the video, not the code. Okay, so let's have a look what we got. The carry cross validation. Remember, we get the, and I've already done it. We get the accuracy in the kappa. So this is the accuracy adjusted for random error. And actually somebody asked me today, you know, why do you sometimes get, one will have the highest kappa and one will have the highest accuracy? And a lot of it will depend on just the, you know, if they're very close together, just kind of the randomness of the data set. But you see here, logistic regression has kind of the highest accuracy and has pretty high kappa, one of the higher kappas, while linear discriminant analysis and SMOTE has, you know, good accuracy and a slightly higher kappa. I mean, there isn't a huge amount of difference, but you know, remember I said tree techniques give you good explanation, but they generally don't perform quite as high on predictive accuracy. So now we've got this information and we've used all this kind of almost posting and, you know, engagement information. We want to do something with the text information. Now we're going to use a library called Sujehet, and let me get this here. And what we're going to do is we're going to wait for it to install a huge number of extensions. We're going to get it to process the pizza request test. And what we're trying to do here, okay, that was a bad idea because it was huge. So I'm just going to pause the video. Okay, so I just showed you like the first one rather than trying to reprint the whole one because I just froze my computer for a few minutes. So this is just the request people make for the pizza. Now, what sentiment analysis does is it will actually analyze text, and based on a vocabulary of positive and negative words, it will actually work out how positive or negative the text is. So this might be some way of working out, you know, predicting the pizza. If somebody, you know, do positive or negative appeals, more likely to get the pizza. And you can have more advanced sentiment analysis, which will actually detect emotions. You know, we'll have what's called a lexicon of angry words or happy words. So we can actually get emotions. So let's just kind of pass pizza request test and let's get some sentiment information out of this. Again, this might take a few minutes, so I'm just going to pause the video. Okay, so let's just look what the sentiment analysis returned. And what it did is it basically, for each of the kind of appeals, it kind of noted the amount of anger, anticipation, fear, joy, sadness, surprise, trust, and also the negative and positive sentiment. Now, this in a way gives useful information. The only issue in some ways is that it actually is not relative, because it's, you know, you might want to divide by the number of words in the appeal to see, you know, how much of it is negative and how much of it is positive. So let's now add to we're going to create this variable called pizza3, and we're going to add these sentiment scores to pizza2. And what we're going to do, this drop is, you know, we're basically adding all the previous independent variables. Now we're adding the sentiment scores, and then the column 22 is the dependent variable. So let's just create pizza3. And let's look at what we get. Let's view the pizza3. Okay, so we have, you know, we have all the information we had before, but we're actually going to get a little bit of kind of sentiment analysis here. So we now have, like, for each of these posts, we have the sentiment score, and then finally will actually have the positive or negative class. So let's have a little bit of fun. Let's go back to the original data and with the request test in it, and let's kind of order them in kind of negative, anger, so that the most angry, the one with the highest post with the highest angry goes at the top. So we're using the order function to order the rows. We're going to do it by pizza anger in kind of descending order, and we're going to take the top 5 of these. So these are the most angry, the angry 5. God, this person was... So this is an actor who missed a theatre audition, and there seems to have kidney stones, and there seems to be lots of kind of profanity. And then we gather from this person that, like, he's being messed around by their landlord, and he's having trouble with the kidneys. And then we've got like alcoholic, got bullied at school, and then this kind of went on and on and on and on and on and on and on. And I've had enough of the anger. Let's have a happy one. Let's have some joy. So let's look at the joy ones. So that's what's the top joy. And it come before you as a hunger man. I don't see about, maybe it's words like kindness, and things of man. Kindness is making it seem like joy. That wasn't as convincing as me, but let's look at positive. So which are have the most positive words? Here we go. And then this was actually quite nice. My partner loves pizza. I want to give him a heck of a smile. About they're trying to like help their partner. Now you notice all these are incredibly long requests, and that's because I said the sentiment is a count. So what we're going to do is, and this is a little bit beyond what we've actually done before, we're actually going to use some word counts. So I'm going to use a function called string split, and this function here, just this kind of text here, just means I'm going to split it via words. So that's just the format of the function, and I'm going to use list apply. And what does that mean? I'm just going to apply this function to each of the items in my list of requests. So it's just going to go through all of them and run this function. We define the function here where we gotta give the length of the request. And again, don't worry too much about it, because this can get very string manipulation can get very complicated very quickly. And we can unlist. And now we've actually got the word counts in each of my requests. And so what we're going to do is we're going to divide the sentiment by the number of words. Now, just saying, if you divide something, some of these just seem to be empty requests. I don't think that maybe people wanted a pizza and didn't have a request. So we're just going to set a minimum to be 1. So that each one has 1 word. And what we're doing here, again, this is a little bit beyond the course. What I've done is we're basically creating, for each of these, we're basically creating a row. So we're going to get it the same size as the sentiment matrix. So I'll just show you what we do. Rep word counts. Let's view it. So you see what we're doing. All we're doing here is we're just repeating across the number of words. And of course, the idea is each of these sentiment columns is divided by the number of words in the pizza request. So now we've got this set up, and we just call something called relative sentiment, which is the sensitive sentiment by the word counts. And we do exactly the same again in that we actually bind the pizzas. Sorry, I've lost it. Here we go. We just kind of create pizza 4 now, and we actually bind the relative sentiment to the other original dependent variables. We also have a column with the actual word counts in them because that's useful information, and then we have the dependent variable. And let's just now see what are the top 5 angry. Oh, I messed that up. What are the top 5 angry requests? Okay, these are kind of, this is where like most of the words are angry. So no, and then let's have the top 5 joyful, most joyful requests. Anyone generous enough? I love pizza. Please be so kind. Pizza would brighten my children's Thanksgiving. Please reach out. I'm a little bit suspicious about the joy category, but let's look at the most positive requests. Pretty cool. We'll pay it forward, and provide pictures of said delicious pizza. Anybody generous enough? So you can see like the difference between the requests with anger and the ones with positive sentiment. Okay, so now let's add with the sentiment scores added. So let's run logistic regression. And let's summarize what is actually significant. So here we have the the usual suspects of the downvotes and versus upvotes, number of comments at retrieval, number of comments at random acts of pizza, etc., etc. And you see actually the sentiment isn't that significant. The fear factor has a slightly kind of positive effect. Ones that seem to show more fear for the future seem to get more pizza. But interestingly, the word count is positive. Remember, in logistic regression, a positive coefficient increases the probability that you have a true class, which in this case is getting a pizza. So the longer the appeal, the more likely you are to get a pizza. And again, we could do the same with discriminant analysis. And we can actually see we've got the linear discriminants, the ones creating the function, but we can actually see the means for the false class and the true class, and you actually see there's not a huge amount of difference. So these are not particularly good kind of ways of distinguishing between the classes. And now let's try an R part. Let's try the tree. And let's visualize the tree. Okay. Let me see what went wrong there. Okay, so we have sorry, I actually seem to remove 3 of the letters from the word tree, but let's just run the tree model and do the graph. And again, you see here this relative sentiment is not actually giving it extra, it's not actually being included in the tree. Now let's do the cross-validation and see if we can see any improvement. We're just going to do the basic cross-validation. Okay, so we ran the cross-validation on the pizza 4, and we really don't get a huge amount of improvement. Now, what we can do is we can actually do logistic regression, but we can do stepwise logistic regression. Now, we can't use the adjusted R-squared because logistic regression works differently. We use the AIC because we fit something called a likelihood function. So we can actually do, basically, we just run it. We have the general linear, we just basically have our model, which was our logistic regression model. So this is what we ran previously, and it's what we ran. We had all the emotions in there, and we will run step AIC, and it will kind of get us a more efficient version of the model to minimize the AIC, which tries to prevent overfitting. And what we could do is we could actually do a summary of this reduced model. And we see what's left was kind of useful. And you see we actually get a little bit, basically what I think happened before is some of these factors were rather kind of collinear. But now we've actually found a model where fear is positive and negative is positive. So these kind of affect the pizza. They're not quite as strong as things like the comments and the number of post variables. But we also have word counts, and that's moderately positive. So again, just to kind of summarize, the sentiment initially seemed like it wasn't doing much good, but when we ran this step logistic regression, we actually found a few slightly significant variables which worked. So now let's just kind of run this model. Now what we can do is we can get the formula with the formula function from the pizza.step function. This just gives us the formula of our final model. And we run pizza 5. And what pizza 5 does, it basically creates a data set based on this model. So it basically includes all the things that were actually significant in the regression. And unfortunately, it puts y as the first column, so we need to actually move this and make it the last column. So we work out how many columns there are. And we now put basically we kind of move it around, so the first column becomes the last column. So you see we have the rows are the same, then we kind of join rows 2 to the number of rows, and then we add columns, and then we add the first column. So now let's rerun our cross-validation using this slightly cut down data set. Okay, and we get reasonable decile lifts. I think the 3.65 is probably a little bit higher than we had before. And again, we have the accuracies around 0.84. So was it worth adding those additional sentiment variables? It didn't really seem to help a huge amount. Definitely adding the word count was good, and we got marginal significance with a couple of the sentiment scores. So I thought it was an interesting exercise, even if in this instance it didn't make a huge amount of difference to the actual overall results.